Hello, everyone. From today's lecture, I'm going to discuss gas power cycles or gas heat engine or internal combustion heat engines. So as a starter, for today and the next lecture, I'm going to talk about the spark ignition engine, which is an engine that you use for your car in general. So that is a chapter 9 of our textbook. So please read chapter 9.3 through 9.5 to understand better about the spark ignition engine. Today, I'm going to talk about air standard assumption. Also, I'm going to talk about the general features of a spark ignition engine. So at the end of today's class, I really want you to be able to answer those 3 questions that you see. The first question is, what are the air standard assumptions? And second question is, how does the actual 4-stroke spark ignition engine work? And the last question I hope you should be able to answer is, can you draw the TS and PV diagrams of the ideal Otto cycle? Before we go further to discuss today's lecture, I really want to review what we learned in the last lecture. So in the last lecture, we learned about the restatement of the second law of thermodynamics. So we learned that the second law of thermodynamics can be restated that no heat engine can make thermal efficiency of 100%. So the maximum possible efficiency you can achieve, no matter what heat engines you talk about, is Carnot heat engine thermal efficiency. For the refrigerator or heat pump, the COP of the Carnot cycle is the maximum COP that you can ever achieve. The second statement of the second law of thermodynamics is that heat cannot be transferred from low temperature to high temperature. Based on those discussions and by thinking about the first law of thermodynamics together, we actually also discussed perpetual motion machines, which cannot be possible in reality. So there are 2 types of perpetual motion machines. The perpetual motion machine of first kind is the machine that violates the first law of thermodynamics. So that type of machine does not satisfy the energy conservation. So even though it may look cool, if that does not follow the first law of thermodynamics, then the machine of discussion cannot be happen in reality. There's another kind of perpetual motion machine, which is perpetual motion machine, the second kind, or PMMM2. That kind of machine violates the second law of thermodynamics. As we discussed just above, if someone claims that their heat engine can make thermal efficiency of 100% or higher than the efficiency of the Carnot cycle, then that is type of PMM2. So now let's get started of today's lecture. As we briefly discussed in Carnot cycle lecture, in general, power cycles should have those 4 processes. The first process is usually the compression process. Then after the compression process, then your heat engine should go through heat addition process. So after these 2 initial processes, your working fluid should be at very high pressure and very high temperature. Basically, it should have high energy. And this energy can be now converted to the beneficial work. So the following process should be the expansion process. Then the remaining heat after expansion process should be rejected. So that is the 4th process, which is heat rejection process. So I really would like you to keep those 4 processes in your mind, because all cycles that we are going to talk about in terms of power cycles must have those 4 processes. Simply those details of each process may be different, but you should be able to see those 4 processes in common. Now, let's talk about gas power cycles. So there are, in big portion, there are two different kinds of power cycles. One is external combustion cycles, and another one is internal combustion cycles. Okay, the external combustion power cycles is the cycle that has certain combustion process outside your engine. Okay, so now in contrast, the internal combustion engine or internal combustion power cycles are cycles or heat engines that have combustion process in themselves. Okay, so in this chapter 9, we are going to talk about internal combustion engines, okay, which have combustion occur inside the system. There are three heat engines that we use in daily lives for power plant or other kind of or other areas. The first engine we are going to talk about today is a spark ignition engine, or in short, we call that as SI engine. Okay, this engine is basically gasoline engine that use the fuel, gasoline as a fuel. And that is a typical engine that we have in our cars. That is an example that of the SI engine or gasoline engine. So if you open the bonnet of your car, then in the middle, obviously you know what that is. You see that type of engine. Another type of engine is compression ignition engine, or in short, CI engine. The fuel of the CI engine is usually diesel. Okay? We don't use diesel engine for car, in the United States, particularly those are kind of cars that we drive, but you can find those type of diesel engines in very big trucks or trailers. But outside the United States, like in Europe or Asia, then you can find a lot of cars that have diesel engines. One big example that I can show about the diesel engine is that big engine that is being used in very big ship. So now, do you see this big piston? And the engine is much bigger than the trailer. Okay, so that is more likely like a four-story building size. Okay. Those two engines, SI engine and CI engine, have a piston inside, and the piston moves up and down, and this up and down motion is converted to rotating motion by using shaft, the crankshaft. So those type of engines are called reciprocating engine because those type of engines should have a piston as a kind of moving part that move up and down. Another type of engine in the combustion heat engine is gas turbine. Okay, gas turbine is really I really love gas turbine because that is, I would say, the high-end energy system device that we can learn in thermodynamics. And it looks like that, and I'm going to discuss a lot more details about this gas turbine and based the gas power cycle about gas turbine later. But in general, we have to learn these three types of internal combustion engines. Now, I'm going to focus on spark ignition engine or SI engine. But before we talk about the SI engine, so let's take a look at what happens inside this type of internal combustion engine in general. Okay, so in internal combustion engines, it should have combustion in the middle of these processes. So what happens after and before the combustion process is the working fluid changes from air-fuel mixture to burned gas during combustion. So what it means is that we need a fuel and we need air in order to have certain combustion process in it. And that is basically the chemical reaction process. And what happens after this combustion process or chemical reaction process, and air and fuel are chemically reacted to produce certain the burned gas mixtures, like it should have water vapor, it should have carbon dioxide, also it should have nitrogen, and so on. So during the overall process, your working fluid composition changes from air-fuel mixture to different burned gas mixtures. And this fuel mixture or pure air, depending on your engine, is compressed during the compression process. Then this fuel and mixture, and right after compression process, fuel is sprayed onto highly pressurized air. Then either by using spark ignition or using spark plug, or spontaneous compression ignition process, your air fuel mixture now combusts to increase its temperature and also pressure drastically. Then your burn gas after combustion should have very high temperature and very high pressure. And that is so high and intense that it's sufficient to rotate your shaft or move your piston back and forth. Okay. Then it should go through the expansion process. And this expansion process is the key process that produces work. And after expansion process, now you have still burn gas inside of your engine that needs to be exhausted. Okay, and this exhaustion process should be following after expansion process. So now, what do you feel after you look at what happens inside this heat engine? We have drastic change of temperature and pressure. We have drastic change of working fluid chemical composition, and we also involves compression and expansion process, and even we have gas exhaustion process at the end, meaning that you have to think about how those still hot temperature gas should go should exit from your engine. So overall, those processes are so complicated. And if you really want to take into account all these complicated processes or phenomena in your analysis, usually you basically may end up giving up, okay? Because there are a lot of complicated features in it. So now we want to do certain simple thermodynamic design or thermodynamic analysis of such gas power cycles. So we need to have certain simplifications. So now we should talk about the air standard assumption. Again, what happens inside the real heat engines are very complicated. So now we want to have those kind of assumptions to simplify our analysis. So now, because we are talking about, we are dealing with gases like air or fuel and mixtures and also burn gases, we assume all working fluid inside that type of gas power cycles is just air. Okay? And this air is assumed to be an ideal gas. Okay? So we totally exclude the fuel part from our analysis. Okay, for now, as far as we talk in our class, as the basic thermodynamics class. Okay, now, so that is the most important part of the air standard assumption. But now we can have one more addition in terms of simplification. So not only your gas or your air being an ideal gas, we also assume that this air has constant spacities at room temperature. Okay? So if we have this additional assumption on top of air standard assumption, then we specifically call that as cold air standard assumption or cold air standard cycle assumptions. Okay. If you obviously you can also assume or you consider that this ideal gas, the air, has variable specificities. So in that case, yes, we still can. And that assumption is called just air standard cycle assumption. Okay. Now, another feature of the air standard assumption is that we don't worry about combustion process because we already excluded the fuel. But this combustion process is replaced by simple heat input process. We just assume that there are a certain amount of heat transferred into your engine during this process. So that makes our analysis a lot easier. And very likely, pretty similarly, the exhaust process of your burned gas after expansion process is replaced by a heat rejection process. Okay, so we don't worry about any exhaustion process of the air. Air does not come out of your engine, but air is still inside your engine. But instead, heat of this air after expansion should be rejected as a heat transfer process. That is the basics of air standard assumption. And I have to emphasize that this assumption is super important. You always have to use this assumption as far as we deal with the gas power cycles in our course. So please remember that assumption.